Yellowcake is a type of uranium concentrate powder obtained from leach solutions, in an intermediate step in the processing of uranium ores. It is a step in the processing of uranium after it has been mined, before fuel fabrication or enrichment. Yellowcake concentrates are prepared by various extraction and refining methods, depending on the types of ores. Typically, yellowcakes are obtained through the milling and chemical processing of uranium or forming a coarse powder which has a pungent odor, is insoluble in water and contains about 80% uranium oxide, which melts at approximately 2880 degrees Celsius. Overview: the ore is first crushed to a fine powder by passing raw uranium ore through crushers and grinders to produce pulped ore. This is further processed with concentrated acid, alkaline, or peroxide solutions to leach out the uranium. Yellowcake is what remains after drying and filtering. The yellowcake produced by most modern mills is actually brown or black, not yellow. The name comes from the color and texture of the concentrates produced by early mining operations. Initially, the compounds formed in yellowcakes were not identified. In 1970, the U.S. Bureau of Mines still referred to yellowcakes as the final precipitate formed in the milling process and considered it to be ammonium diuranate or sodium diuranate. The compositions were variable and depended upon the leachant and subsequent precipitating conditions. Among the compounds identified in yellowcakes include uranyl hydroxide, uranyl sulfate, sodium parouranate, and uranyl peroxide, along with various uranium oxides. Modern yellowcake typically contains 70% to 90% triuranium octoxide by weight. Other oxides such as uranium dioxide and uranium trioxide exist. Yellowcake is produced by all countries in which uranium ore is mined. Further processing yellowcake is used in the preparation of uranium fuel for nuclear reactors, for which it is smelted into purified UO2 for use in fuel rods for pressurized heavy water reactors and other systems that use natural unenriched uranium. Like heavy water reactors, purified uranium can also be enriched in the isotope U-235. In this process, the uranium oxides are combined with fluorine to form uranium hexafluoride gas. Next, that undergoes isotope separation through the process of gaseous diffusion, or in a gas centrifuge. This can produce low-enriched uranium containing up to 20% U-235 that is suitable for use in most large civilian electric power reactors. Some nuclear power reactor designs such as CANDU heavy water reactors use natural uranium oxides with